I should test the microphone. Oh, testing microphone. Circular road. So last time we had left and we had been working on this, which looks a lot like the 2D example that we saw right before. The week before, we had done a 2D example, which was basically cut through our domain. And we had exactly the same boundary conditions, if I remember correctly, right? No flow under the footing, or half the footing, because we were using symmetry. In that case, this case, it's axis symmetry, so we will always have a no flow boundary here in axis symmetry. Problems involving consolidation or flow properties. And so the water can go in two ways. So the formula will be a bit different.
Excuse me, this is the same principle that the GeoStudio used in the analysis?
Yeah, yes. The only difference is that we are doing finite difference. They use finite element, which is a different way of setting up your matrices, okay? In the end, when you go to steady state, mathematically, in the code wise, it ends up looking very similar, to be honest. What changes the most is the coordinates. So, and even here, we can have variable coordinates in X and Y, variable X and delta X and delta Y. So that will add some complexity if you incorporate that. By default, for our purposes, we have stuck until now to constant delta X and constant delta Y, just because it makes some computations easier. But remember that if you want to look things over a wide area and you have locations where with a higher concentration, sometimes computationally it makes more sense to take the difference, the delta X and delta Y, as different values, but it means that you no longer, even a uniform soil, you no longer have a constant little R in that equation and so on. So we had been working on our spreadsheet. Right, so if you go over what we did. So we did the calculation of the stresses. We had said, so here, I had set up a load, and here you notice that it's offset by by half the interval. So the interval was 0.1. But I offset the coordinates here because I'm replacing the stress by a concentrated load at the center. Okay, and here I just did it mathematically because it was a circle, it was easy to calculate the load at each point, right? So these are forces for squares that are 0.1 meter by 0.1 meter, okay? Because that's the spacing I chose for the loading. Note that that spacing for the loading has nothing to do with the spacing in the mesh of the finite difference. Okay, this is just because I want to integrate my load because we're using the Boussinet method for the accumulation of the stress resulting from concentrated loads, right? And because we have an arbitrary shape, we use this. Now, the beauty of this is that you could generate a stress distribution that is not constant. Can have a gradient, can have different values, different areas. You can have a family of buildings on a site with different loads at each footing. And you could distribute it with a similar manner, even if your cross section that you're going to analyze on a plane is somewhere in between, you could use something similar. And in that case, instead of using an equation to generate this, you could take an image file and associate a square to a spot in the image file and then associate coordinates X and Y like I did here, okay, on the plane. So keep that in mind that here it was easy for a circle, but you could do that for any kind of shape, for an embankment with sloped sides and things like that. You could use a similar approach to figure out the stress distribution. So if you want to do a map of settlement when you build an embankment, you could use something like that, even if you don't want to use a fancy finite element modeling for settlement, which most people don't do in practice, right? We use the Boussinet because it has been shown to give reasonable results for these calculations, so people still use it to this day. Okay. In terms of stress distribution. So in our case, this is where we had re-expressed the load, okay, using offset. So we just went and found our index. We had 483 points because there was based on the number of rows and columns that we had here, right? We had 22 rows, 22 columns, which gave us a total of 484. But because we start at index 0, we subtract 1 to get 483 is the maximum index, with the minimum being 0. And we do the same thing for our domain for finite difference, where we have 91 rows. We have a delta Z and delta X, or delta rho in that case, because we're going along. Delta rho of 0.5 meters and delta Z of 0.5 meters. Okay, so that's on our axisymmetric plane. And so we had expressed those loads. So this is just a remapping, okay? On here, the load here value that I have on column D is just, so if you look here, as we had seen, it's just an offset. So we're taking our loaded area, we're looking just at the cell that corresponds to our row and column. So all this column D does, all this function does, is just look up my current index and it just maps. It says this is this one or this is this value. So it's either 0 or 0.5. Okay, that's why we have 0.5. So it's just a remapping. And we're just putting them in a string, in a long string. And we did the same thing with stresses. So here the stresses will go, this is our plane, where we have x's that go from 0 to 45. We have 91. So count 91 items, 91 columns, and we have 17 rows. And this is the values that we have here, basically, 91 columns and 17 rows, for a total of 1547 indices, minus 1 because we start at 0 again. So here, what we're doing is, so this is mapped to this, the X and Y and Z are mapped to this. Notice that the Y is always 0. Why is the Y always 0?
Okay.
Because I'm looking, exactly, we are looking in this particular case, we're looking from the top. So this is my loaded area. My plane that I have is really, it goes from 0 at the center of the circle to 45 meters here. So when I'm looking at my plane, I'm in reality looking at the projection of this. So I'm just looking at the projection on a separate diagram. I'm looking at the front view, and above I have so that's the top view, and this is the front view, basically, of just that. Okay? So we have half the cylinder here, sitting here, and distributed below. Okay? So that's why we are, so the Y is 0 because this is X. And obviously, yeah, so we have X and we have Y. And here we have rho in the horizontal direction and the depth Z is going this way. So here oops, sorry. Wrong direction of my arrow. So the X direction, the rho direction is parallel to the X direction, but we call it rho because it's true in any orientation. So it's really the radial distance that matters here. So that's why here we had the X, Y, and Z, and we defined the load QZ. Now here, I have delta PZ, so DPZ I called it based on this. As I was telling you, it can help you a lot in a spreadsheet to define variable, because imagine if you have to start implementing this. Well, there's two ways to write the equation, right? One where L5, that's the distance in 3D. And there you can see that it's R squared plus Z squared, where R squared is X squared plus Y squared. So L is basically or L squared is basically R squared plus Z squared plus it's basically the L squared, X, Y, Z squared. Okay. So how did I define those values? Is what's matter. So keep in mind that I'm here at H9. Okay. So I have defined L, which is the square root of X underscore minus X of load. So there's two values of X here. We have the X along our value and the X of the loaded point, right? So here, what I did here, I have a transpose. I basically took the load, which is the remap loaded area, which have X, Y, and load. And I mapped there transposed, okay? So this is the way to iterate because I want to do a summation. So on a spreadsheet, I cannot just do a loop easily, right? So instead of doing a loop, what I did is I transposed that in that direction. Okay? So I can calculate the distances more easily. So here I will be able to calculate the distance between that point and each of the loaded areas. So how do I calculate that? Well, I have defined dpz, which is basically the equation that we see above. Okay, so we have 3 times p and z cube. Oh, yeah, I first defined 3 times p over 2 pi times z cube over L5. Okay, so we have one term and then the other one. P is what? P is H4 is basically the load, the force above. So you see it's H for that particular cell where I was, which is H9, right? Keep in mind that we are at H9. That function will change basically based on the position of our cursor. Okay. But because I am at H9, it takes H. H will vary, but the rule 4, because it has a dollar sign, will always stay there. So it's the load that I took from my loads map. Z cube, the Z is what? Z underscore is D. The D is fixed, so the position is D. This is Z, and D, this is Z, right? The depth at which I want to calculate. And 9 will change depending on which depth I am at. So each row here will have a different value of Z. It is its values. And then we have L, which subtracts X minus X load. And basically it's at the same row, the X and the X value at the top of the same column. And so it's using the difference, which is the same thing for the Y's and and the same thing for the Z. It's Z minus Z flow. And so we have defined all of them. So I have defined all these values in the spreadsheet itself because it's much easier as named variables, right? If I need to change it, if I made a mistake, I change it once and it changes everywhere. So this is a lot more like programming than trying to do it in the cells themselves, right? One of the key problems with spreadsheets is that it's easy to change a formula, think you applied it everywhere, but you didn't notice that you stopped ahead of, and it's not applied everywhere. So now you have a formula that breaks, right? To avoid that danger from spreadsheets, the best way to implement it is by defining your variables like this. And then you can use it in the format, see? So I just say DPZ here, and I have some values. Now, just for fun, before we do, I'm going to, so let's map them first, right? Right, what we want to do now is just, map them. And this is what we're doing here. Here, we're doing the same thing that we did here, okay? Where we mapped or the here where we mapped the stresses that were in 2D, we mapped it in the sequence. Well, here we do the same thing. Where we just take the column index, so the variable QZ index. If I look here as row times the number of columns, which is 91, right? So row 0 times 91 column is going to be 0 plus the column. Okay, so if there's 91 rows, but I'm at the first column, the row index is 0 because we're started at index 0. So we start 0 rows plus the column. So for all of the first row, it uses 0, so it just takes the number of column. When we get to the next column, now the column index is 1. So it uses 1 times 91, so it takes 91 plus the column. Then 2 times 91 plus the column, and so on. So that's all it does. So that QZ index, so it says, the question here says offset QZ, and if you look at QZ, QZ is here, it's a single cell, which is this is the cell that is referred to, QZ. It's that cell, so we need to move 1. So I needed to say +1 in my index, so index +1, because otherwise it would start at 0, and the cell was the header. And so it offset, the variable is QZ, I want QZ index +1. Don't move the column, because I want to stay here, I want to be here. I start at 1, so I start at 1, the index +1 comes here. And then I have 0 movement lateral, and then 1 term, so 1 and 1 are because I want 1 cell only, so 1 row, 1 column. That's the 1 and 1 on the offset command. I just did that everywhere. Okay. If we look at this and we were to conventional format. And it's a little bit like what you expect the stress bulb to be. I wonder what it would do as a percentile. It will probably stretch out the format, conditional percentile, what would it show? It's not really. You can see a little bit the shape of the distribution of the values, right?
Excuse me, so as you go to this way, so the stress decreases
Yeah, as we go away from
from the center of the
it's the
load.
maximum below, right below the load is the maximum stresses.
Okay.
And it decreases with distance, as you expect.
Decreases like based on this one, in term of, it's not linear.
No, it's not linear. It's based on that equation that we have. That was for a single point. Now, what's interesting is that if we go to the plots, if you look at in 1D, this is the equation that you get for 1D. You had a crash? No. Had a crash. Crashed everything. Cover. Here. Okay. If you look at the plots, if I take that first column here, and you take the calculation done by 1D. So we could do it at different times, but it will that we'll do later, but it will just match 1D. The problem with 1D, as we saw, is that it assumes drain, fully drained, fully drained. So we can do it at a different time and see that they change differently. But what's cool is to see that our integration, despite its limited size of 0.1 meter to 0.1 meter, it gives it the same thing as a closed form solution of 1D stress distribution, right? So we can see that because at a position of 0, we get exactly the same curve as we get by doing the using the formula for 1D. So our little stress distribution, we have higher confidence in its value now because we can see that we get the same value under the center of the foundation. Okay, so so what we did last time, let's see. We're putting. So last time, if you recall, we needed to define a time 0, right, an initial condition, which is basically what we have now. We're going to copy that. And then we need to develop for the different time periods that we have here. Right? So what was for our time interval?
Excuse me, the time after applying the load, like the time series, the one that you like you are talking about, it's, let's say, after like minute, like time.
Yeah, we apply the load.
Yeah. So you can do like this the graph, or this Excel sheet. It tells you like after like 10 seconds what will be the stress, or
Well, we would have to set our time in, we would have to set our time step to be small enough, right? In our case, I think we were looking, I think we can use the same time step that we had here. 112 was 1 month, but if we used 2 weeks, I believe, right? So we use the time step of 2 weeks for our 2D analysis, right? So we could do the same thing in this particular case. Look at our variables. So we did not define CV 1.1. That's meters squared per year. Okay, that 1.1 meters squared per year. Okay, and this is our delta T, which is 112, so that's a month over 2. We wanted to get the same type of result. Now, let's go back to our presentation because we have to remind ourselves of the form that our equation had. If you will recall, we did not have exactly the same equation as before. So when r equals 0, we have this equation here. So we need to have a radial or horizontal equivalent. So we have, in this case, rho is our parameter. Okay, in the radial direction, we have rho r. And then we have, because it's a uniform soil, we can use a single value here. And then we have rho v. And in our case, if we say that CV equal to CH, which is definitely something we should do it. Right? Two different variables. Of this. So that we can now define our variables. Rho v is CH delta T over delta R squared. So that's delta rho here at 0.5. That one was E. That one was CA, V is C delta T over delta Z squared. V times delta T over delta Z squared, right? and it's smaller than 0.25, so we're good. So we still have the same kind of rules that apply here. And that is equal to CH times delta T divided by delta radius rho squared. Okay. We have defined our values. So the general equation is different. So when rho is equal to 0, so we, because of axis symmetry, one thing that we can say is that at the axis of symmetry, we have a gradient that is 0, right? And oops, sorry. Apparently, I had not run I forgot that it had crashed before. So when rho is equal to 0, we have a problem here because we have a term that's divided by r, right? When the radius is 0. We have a term that's divided by r. So what can we do here? Well, we know that the gradient is 0, right? Because we have axis symmetry. Because of the symmetry on both sides, the pore pressure on both sides is equal, so the difference is 0. If that difference is 0, okay, then independently of what this value is, this will be 0, right? So that's why we can set this to 0. And we can forget about that term doesn't have the 1 over r term, and it boils down to what we have with the usual variables. And so we only need to care about the general equation. On all the other terms, and at the r equals 0, the term 1 over r disappears, and the rho h basically becomes the we have I plus 1 and I minus 1, which are equal to each other. So those two will be added. That one will remain as usual because it's not necessarily on the axis. So we'll need to define different values of the cell. Okay, so we have at n plus 1, and we use just the explicit method because it's easier to set up on our sheet without building a matrix, which I hope you realize that the matrix would be challenging to set up. Okay, so let us have our initial conditions. So we have our initial conditions will basically be the plane stress matrix, okay? So we placed here as values. So that later we will be able to refer to it. Okay, so this one we can always repaste at any point in time. And we can have our generic T next. Let's see, the next time step, this is where we do our calculations. I'll go to D, 1 and then 4. There's 4. You could just took our values. Yes. Running too much stuff, I think I have to cut down what I'm running, right? Down. Clear loads. Those the strip footing one. Just taking formulas. So now we need to define our functions. And then So one minus two rho H minus two rho V. Notice that we have a third R coefficient, right? We have the vertical, horizontal, but we also have the radial, which is different, not delta R squared. It's two delta R in this particular one. So we have to define that one, which we have not defined before, but it's still CH.
Excuse me, like at the beginning of those slides, R was equal to zero. Okay, and from that one, you get the point like the symmetries, the answer for the symmetries will be zero. But if I need to look at it in terms of math, any number divided by zero, it's infinity.
Yes, but you don't care what it is because it's zero. It has no value. That term does not count. It's zero. Whatever it is, however big it is, you multiply it by zero, it's still zero. Doesn't matter how big it is. 300,000 million times zero gives you,
It will be zero, but the coefficient itself, it's
it
infinity.
doesn't matter. The coefficient is infinity. So 300 gazillion times zero gives you,
Zero.
infinity times zero gives you
This one, not, it's undetermined.
zero. Whatever the value is, infinity represents any number, however large it can be. It can be one, it can be 10,000, it can be 700 million, it can be 10 to the power 75. It can be as big as it wants. The moment you multiply it by zero, it becomes zero. Doesn't matter how big it is. It's not zero divided by zero in this case. Think of it in terms of whatever, however large it is, you're multiplying it by zero. Okay? So there's different ways of handling infinity, and this is the only logical way in this particular case. Okay? Because it's not so much infinity as it is a
Dimension.
It's a singularity at that point. So singularities are rarely really physically defined. So, but whatever, however large it can be, the point is that you don't have a gradient. It doesn't matter because there's no gradient. So that term is irrelevant. So we said it was equal to CH times delta T over 2 times delta
Delta R.
delta rho. So where we have it here, I think. Because we had R used for different things at different points. Yeah, the radius is delta R is 0.5 meters. Video. Yeah. I am not correct, incorrect. It's the H delta T over 2 delta R. Yeah. And now we have here to carry these values. Let's see if we can. Okay. So we'll use it as a reference to do our calculations here. Now, things will change at the boundary. We will have, actually at the boundary, we will have different values because we have a upper, lower boundary as well as left. And those are, actually the upper and lower boundary will be easy because we have, so the upper boundary is no flow. The lower boundary is zero. Right? Because it's controlled head. We have set our pressure, excess pressure to zero at the edges, right? This is a free draining problem. So we set this as oh, do I have here initial conditions? Ah, yes, I accidentally removed the page. So insert sheet, I called it T next. So T next will be um, let's do the general equation first. Here we have zero at the top and zero everywhere at the bottom. Okay, so we have established our boundary condition. I could have set a text variable there too. Okay, here we have top no flow. Here we will have left no flow, and here we will have top left no flow. Or no flow top left, no flow left, no flow top. Okay. But what is our general equation? Our general equation is, we can define it here just in T next. So we have axis symmetric equation. And that one will be, so we're F6, so it's 1 minus 2 times rho H minus 2 times rho V times. This is where we now have to go and pick our location. So we are F6, we'll go to initial conditions. F, we said we're at F6. F6. Right. Uh, First, let's cancel all of it for now. Let me make sure that initial condition or previous. Let's call it T previous. Okay. And T previous will have our initial status here. As values. Okay. Sound a bit better. We adding. Next, we had axis symmetric equation. That's our general axis symmetric equation. So we said it was 1 minus rho H, minus 2 rho H, sorry. Two rho E times E rev. You have to be the same cell, so it will be F6. Okay, so I put without $sign because I want it to be from the sheet T prep, but I want to move with my cell. Plus, let's add it as is. So that we have a nice save point. Then F6. TPEV. Call it TPEV for now. Okay. And now the cell it became capital F6. I knew because they had not capitalized, so I detected that I made an error. But it's not bad to build your equation a little piece at a time to catch errors as you make them, because you will make them. Rho H times again T PEV. I'll change it later, but so we're looking at that's the horizontal. So we need the two neighbors, right? So the neighbor to the I should actually let's so that actually it may be easier to define neighbor left. We'll define neighbor left, which will be E6, okay? And this one will be defined for just for this one. For T next, okay? Then we will have neighbor right. The previous to have that it will be J6, G6, and that's so I'm defining those so they're easier to put in formulas, right? Otherwise, I always have to look at G6 at the rows and columns. So to avoid having to do that, I just define what is the left and right neighbor and so on, okay? Then we add the neighbor up. And that's again the previous. It will be F5. And the neighbor down the previous F7, right? Neighbor down. Go. Oh no, that's okay. left, neighbor right. Neighbor up. Yes. F5. Down, neighbor down, which is the previous. Neighbor down, neighbor left, neighbor right, neighbor up. And we have to have neighbor center, which will be at T previous F6. So that was just to refer to the previous sheet, but to have an easy way without looking at the rows and columns each time, which is how you make so many mistakes. And that way, if we need to change, we change it once. So we can go back here and say, that's the neighbor center, right? Neighbor center. Because it's UIJ, so it's the previous neighbor center plus row H times neighbor left plus neighbor right plus row B times neighbor up plus neighbor down. Not finished, but and now we have plus row radial times okay. One over radial distance times neighbor right minus neighbor left. Because on the left we have smaller value. So it's the bigger minus the smaller. 1 over radial distance. Okay, and radial distance is not defined, so I will define radial distance as I'm F7 now, okay, as F1. Fix the row, that's only valid for me. Let's say RD 1.5, 1.5. Okay, so radial distance is defined. Way. 1 over radial distance, okay. Axis symmetric equation. Metric equation, so something is not defined. Our row H, row V, row R. Row H. What other equation did I use? RD, neighbor up, neighbor down, neighbor left. Neighbor left, neighbor right, neighbor up, neighbor down. Oh. Works, why take this one? Oh, that fixed it. Okay, so we have this defined for our values. For most of our equations, right? Hope it looks good everywhere, but it's. And so we have our. Let's compare F6 is 35.5 at the next time step. F6 was 42, so it is going down. That's a good sign. It's what we expect. But further out, it should be going up, right? At 0, so here, 5s. 6.3, 6.5. Yeah, it is going up immediately adjacent to the loaded area, so it makes sense in terms of diffusion. So we need to define boundary left, boundary top. Also, we're going to add no flow left. Or no flow L. So no flow L, I will define partly with this equation. No flow L will be the same equation, except that I remove the part that is radial, right? And then left term, we don't have a left more term, so it will be 2 times right. So the right neighbor, right? Because we're on the left. So this one. This one will be no flow left throughout. No flow up will take the same form as the general equation. No flow up. No flow up will take the general form, the same form as the general equation, except that neighbor up will become neighbor down. We have 2 times neighbor down, but You can also keep it as a summation. No? So this one will be no flow up. And finally, we have the last one, which is the corner. So that one is no flow left up. So we will use no flow left as the basis. No flow left up. And we will call it, we'll replace up with down. So this is no flow. That's OLU. Sounds good? I think we got it, right? Confidence that we got it? Says we got it 100%. I don't see a lot of faith here. Not much faith, not much faith. Okay, we're going to have to start doing our copy pasting things. This is time previous. I will duplicate the sheet. Well, you rename to T0 because that's our initial condition. Name this to T spread. And now we needed to run the macro, if you recall. I should still have that macro installed. So, options, macros, tools. So yeah, I have iteration, iterative programming, iteration module. So I do have my my main, which basically runs my macro. So let's add here a button. Shift to view, toolbars, run controls. Nice. Cooler. Okay, and we need to associate execute action, a macro. No. Ready to go? Let's try it. Copy line mode, go. Error. Oh no, we start with an error. How come? You need to define an iteration source range defined with the name iteration SRC. Haha, we forgot to define our stuff, right? Okay, iteration source. What will be our iteration source? Our iteration source, and this is the reason I made sure to copy that I was copying the the values here. Basically, we want to copy this. So this is the range. Okay. So we will call it iteration SRC. And we're going to move it here. We want that to be pasted here as a single as value. So this will be iteration BGT target. I'll go to my macros. I should add some kind of helping dialogue, that's for sure. But I also have iteration, max iterations, and iteration indicator. Those are two things that I want to set up before I start. So this one will be max iteration. Say 2, if we want to step 1 month at a time, because we set our time to be 2 weeks.
Yes.
Right? So we want to advance 2 weeks at a time. And or half a month at a time. And then we want to advance by, we will keep a record of each month until the first year. And then we can keep every year until 15 years, right? So then we advance by 24 till we reach the first year. Just to keep record, I choose to keep record by making a duplicate of my previous sheet, okay? The T previous will become my record. So this is my iteration and this is current iteration. This is just iteration indicator. Okay, so this one should show what iteration we're at. Okay. So ready for month 1. It's going to do 2 runs. 2. Yay. 1 month complete. So now the T prev, I can duplicate it. And I call it month 1. Okay, so we have 1 month, so times 0. So that's okay, so times 0, we have 50, 45, 32, then we have 43, 39, 29. So it's moving in the right direction, apparently. Here we have zeros always because it makes sense, right? These are controlled boundary conditions. So now we're going to do month 2. So we run again, bang. Okay, finished running 2 months. 1 month, 2 weeks. So again, T previous, we duplicate. That's month 2. Run month 3.
It's without it changing the alteration.
Huh?
You are not
It's changing.
keeping them too.
It is changing. The thing is, you only see the end. Page sheet, because it doesn't refresh every time. This is month. You can see how it's changing from month 2 to month 3. The values are going in the expected direction. So month 4. And then month 4. Month 5. Always duplicate tpref. Six. Then 8. Variables. Um, Month. Getting there. 9. And another way to do it would be to copy the T next and referring instead of the neighbor up, neighbor left, being to the previous sheet instead of being a fixed sheet, right? That's another way, which you can do in LibreOffice, but not in Excel, that one. So, but, and then you would not need to run the macro, but you need to keep every single sheet. You might run out of memory and have more crashes though. Memory tends to be the sore point. So we have month 9, and on month 10, almost of the first year, we can start using the rate. So this is month 10. Seven. Now we're gonna go to year one. And this takes us to year one. To yeah. And year one. So now we go to increase this to 24. Okay. Go here and duplicate. Two. Three. So you can see how doing the same thing through a little program of yours might make it a bit easier to mark the points that you want to save, right? If you want to save a certain time steps, you could have a list of time steps you want to save. Or you could make a macro here that does this part for you, right? But it involves programming one way or the other to add a bit of ease of use, right? So therefore, but I just wanted to show you how you can use these. And to get our, now for fun, so we may not do it right now till the end, but I will have a save here. And just to quickly open the previous, the strip footing. And just have a quick look at, so we have month one. From the same. Well, let's have a look at, first of all. Let's see. Let's see what's going on. Wrong screen. Yeah. Yeah. So we go for both cases. If I go to times zero times zero. So we do have a difference in terms of just initial pore pressure distribution. That's important to know, right? 50, 50, 25, that's exactly the same at the very surface. But if we look a little bit below, already we, under the circular load, we don't get as big an initial pressure with that as we get with strip footing. Okay? Because in strip footing, we have an infinitely long loading in the direction perpendicular, while the circular load is it's finite. So that shows in the 1 month, it should show also, it should decrease faster. Okay, so 46, this one is 43, that decreased pretty fast. And consistently, what we should see is a faster decrease. This maintains a lot more. This went down already to 33, 31. It goes down much faster for the circular footing because the water can evacuate in all directions at once. Okay? So that is definitely one fun thing that we can see from the two, the axis symmetric. Now, another thing that we can do is compare it with one D. And here again, one D should be slower. It will be the same kind of thing that we had here. So one D is slower, but it starts with a different initial pressure than the strip footing. So, but it will be slower also than in the same manner that the strip footing was smaller. Okay, so I'll leave it for now, to that point. I'll upload that spreadsheet. And if you want to play with it, you can, in the one D, I set it up, the beginning of one D. And you can plot different things. Shows you basically the basic procedure that we would use to solve these problems. And of course, once you have one problem set up, now I build these spreadsheets with you here. But you can keep the spreadsheets like these once you've built your spreadsheet. So similar types of problems, even if it increases in resolution, you could set it up and solve it for different timeframes. I mean, you don't need to stop at every month, right? I did that because I wanted to really see, okay, I wanted to see the progress at 1 month intervals, but if you are only interested in seeing midway and some bigger intervals, then you do the number of iterations that you need, and it will do those iterations. Right? So that little macro that I made, all it does is copy paste for you, right? But I thought that it was a generic enough and something we need to do often enough in practice in these type of problems that it becomes very, very useful tool to run without going into other programming languages. If you feel comfortable in a spreadsheet and you don't have a very, very sophisticated problem to simulate, this could potentially be all you need, right? Or at least certainly a benchmark that you can compare other techniques or your own program. If you want to code, you can still do this to set up, to validate, the same thing, the same way that you want to validate with a physical model. Sometimes you know that your code is working as intended, you can validate against this and then move to the next step. That's one of the things some of the things that you can do with this, okay? Now, you may have noticed the glaring problem with the examples we've done till now. We'll have a very quick break. I just need to go and be back, and then we'll wrap it up. But we'll wrap it up by starting what we want to, I want to talk to you next time, okay? But before I go, what is the biggest problem with the examples we've done till now? No problem, right? What about the boundaries?
Like, because the neighbor, we said, like, when up and like neighbor up, neighbor down.
That's the same way you would do it in programming, I think. Neighbor up, neighbor down, we just use it as a reference. But if you're programming, you would define a variable that points to your neighbor. So I think that wasn't easy, but it's not the biggest problem. What was similar in all the problems we have solved that maybe is not what you would like to do in a real life problem?
The boundary.
Well, not really the boundary. It's more the geometry. Don't you think the geometry was boring?
But this is the typical that we have the circular or.
Everything was rectangular.
Yeah, but this is what we will face in the real life. Is that circular or like square or rectangle?
Yeah, it's not this, things are, I mean, let's not go too circular. We're still going to have a mesh, so everything will be broken down into little cubes, right? But even if you break things down into little cubes, wouldn't you like to be able to manage arbitrary geometries, say a dam. Would you like to be able to do the steady state, find the flow line going through your dam? No, oh, you wouldn't want to do that? You're happy with just having rectangles?
No.
Wait, what do you mean? Let's say I want to find, I have a dam that has different components. I have different hydraulic conductivities in my dam, and I want to know where how the flow, the surface, the phreatic line will go, right? Sometimes you need to find that to calculate slope stability. You want to know what your phreatic line will be. You want to know what happens if you change the length of your, say, of the filters and the drainage blankets and so on, right? But that geometry in the spreadsheet, how do you handle that in the spreadsheet? Did you do it on a spreadsheet, or you absolutely need a finite element program now to do that?
I mean, you possibility to do that.
It's arranged by setting down like zeroing
Again,
rows.
Yeah, but let's say you want a fancy geometry, you want different materials that have different. Maybe you have a little soil lens here, you have this shape, nice.
Well, if you're always iterating and merging, you would then bleed out that effect.
Okay, how do you import that geometry with different soils that have different shapes?
Well, you have to manually use the initial condition and update it.
Not just the initial condition, but you have the material properties, right? Your hydraulic conductivity is changing. You want to associate hydraulic conductivity with each cell. How do you do that? In a spreadsheet, how do you adapt that geometry?
Like the Minecraft.
Is it super difficult to do?
Yeah.
Okay, I'll just have a very quick break and then we'll start talking about how we handle that. That's what we'll handle next week.
so that means it's the variable you keep now, in this case, the variable, just the material.
Well, the material can have different variables, right? The hydraulic conductivity, potentially density, thermal conductivity, all kinds of things, right? But what I'm saying is that it's boring if we're limited to rectangles. I find it very boring. I want to have fancy shapes. And so we'll start talking about it and then we'll finish next week talking about it and running some nice sexy example.
You know that the material flow network has something called an initial state analysis. Because I use finite elements before, and at t is equal to 0 initial state, the finite elements never will calculate the slope under the weight and that is
So let's see how we.
and make it as origin geometry. And that those origin geometry with elements at the initial stress.
Yeah.
Yeah.
Can I ask you a question about that? It's related to the flow of contaminant in unsaturated soil. One of the equations, it's called Richard equation. Like for this one, I have the equation itself, okay? And in YouTube, I found like
Or
they
maybe
built a
train
model,
it.
like just simulation of the models. When I used this YouTube, like
Forget about
video
or the
presentation, or you didn't prefer that? Like how you here, you have the color coding, you show like at the center, it's like concentrated, and as you go, the load decreases or the color change to the same. It shows the
You build the presentation how you find in any way that you find effective to convey the message you want to convey.
what I will like do in the presentation is just talk, like just this is the equation, those are the variables. Like
You can find some images or generate sometimes some images. It's possible depending on, but I mean, I don't want to impose a.
concept at the end,
You do a presentation and you find a way to do the presentation as best you can.
In the presentation, should I introduce the method step by step?
You should do as much as possible for us to understand what the method is, right? The goal is always to be able, for your audience to be able to implement your method. Okay, that's ultimate goal. Now, some things may be, so if you have a step-by-step breakdown for yourself, it's not bad to show that step by step.
But it's very long.
Then if it's too long, you summarize for the presentation as much as you can, right? You try to convey the essential, okay?
And for the reports, should I show them step by step? For the report?
Yes, it's good to have a step by step to be able to explain everything if you possible. Yeah, not bad. So when you get the software package, okay, like finite element method to solve it. Solving the finite element method is usually fairly simple. I mean, there's complexities, like when you start talking about soil plasticity, then at each step you need to check where you are in the state of stress, and it will change the stress strain relationships depending on where you are. So you need to keep a history, and that adds some complexity. But in essence, between each step, all you do is invert a matrix and run it. And it's similar thing in finite difference, right? We're inverting matrices. I mean, for the explicit, you don't need to invert even a matrix, right? You just you just solve or apply multiplication, right? That's all you do. And for the implicit, then you need to invert the matrix and do a multiplication. But that's the core of these methods, right? And yet they come and sell you these packages that are super expensive. And you should feel a little bit skeptical. 99.9% of the programming work that goes into these packages have nothing to do with solving the method. The solving part of the method is the easiest part. It's been done a long time ago. And even when you introduce new constitutive models, yes, you need to check validity of things like that. But even that part is not the hard part to handle. As you can imagine, other than copy protection, which is disabling parts of the programs intentionally for people who don't have the license, right? That's a big part of effort that is frustrating from a developer's point of view. But most of the effort is in the tools for you to build the geometry and then building the matrix, okay, based on that geometry, saying, okay, this and this is its neighbor to the right, this is its neighbor to the left, this is the neighbor to the, figuring out all these things and building the matrix. That is the effort, right? So you're a student on a budget, right? You need to solve some things for your research or for a design. Point is, you're on a budget. You may not have thousands of dollars. So what can you do to achieve similar degrees or similar results with the tools that you have in the spreadsheet, basically? Okay, so today we're going to look at what we can do to use to solve for a simple dam problem. And I mean, this one will be fairly simple. You can complexify it easily by adding materials. And that just goes into your solution. Okay, so I will show you, so we'll download a software called LibreCAD. It's an open source software. It's available for Linux, Windows, Mac OS. So this one is definitely a tool that you should have. It lets you do 2D CAD. And only 2D, so it's not as powerful as AutoCAD, but its native format is DXF, which AutoCAD can open directly. So drawings that you make with this can be opened in AutoCAD, usually without a problem. But this little program has one advantage, is that it has an export to image function. Okay, so let's say you build the geometry, you assign colors to different materials. Okay, so the key here is to really assign the colors. This one has only one material, but obviously you can do this with multiple materials just as easy. Okay, the key is to assign different colors to different materials. Okay, and the way I do it is I use a hatch pattern that is a solid color. And I remove all lines after I'm done. I remove all lines. I just keep the layers. So I turn off the layers that have the lines, and I just keep on the layers that have the color. By doing that, I can then export it as an image, and we'll go over it, and I'll show you how to use the software. But there's a very special image format, that is the XPM, a pixel map for the X server. So that's that's been in Unix, Linux systems for a very long time. And the advantage is that each pixel in that file format, each pixel is an ASCII character. Each color is an ASCII character. So it assigns, so it's basically a text file where one line of text corresponds to one row of pixels. It has a little header, a short header to explain which color is represented by which character, blah, 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 blah. That lists the number of colors and the size, and then one row of text. So by default, it can use one character. If you have many, many colors, it can go up to 2 characters per or more. So that would be in your definition, your table definition of colors, right? Once you've read that. So because it's characters, you can actually import that text file in Excel, skip the header row, and you just have rows of characters. And you can parse those into cells, and bang, you now have a cell with a character. Now, if in Excel you use the match function, and you match a character and you have a little table, well, you say, well, this character is this material and it has this horizontal hydraulic conductivity, vertical hydraulic conductivity. So you can now have sheets where you assign material properties at each pixel based on that image file that you've imported. Okay, so there's no limit to the geometry you can have. It can be very complex, and you can still import it into the spreadsheet like that, like a string of characters. Okay. It doesn't look nice, but then what you do is with the text mid command, okay, you can parse the data into the individual cells. We'll go over this process next time. Today we'll just go to see where to get that. But this is the kind of output you can get if you use a step, integer steps. You can basically get equipotential lines. Okay, for that, this has solved that problem. It was a uniform soil, so it was fairly easy to solve. So I'll try to prepare a nicer geometry for next time, so we have more materials. Okay, so it will be a bit cooler. But this is basically what you get otherwise. And if you keep track of the elevation, right? Remember that pressure head is, this is your hydraulic head, right? These are jumps in your hydraulic head. This is how we generated this. But if you do your hydraulic head minus the elevation head, so you do not just subtract based on its position, you can have a column here with the Z or the elevation. You subtract the elevation from it, you get the pressure head. And if you get the pressure head, you can say, if you're below zero, give me one color. If you're above zero, give me another color. And again, this one was a boring because the elevations were low, the elevation difference wasn't too high. So this, we're gonna make a more interesting example. But you can have basically, if you say that the pressure head is larger than zero, then you're below the water line. If it's smaller than zero, you're above the water line. So you can use this to identify your phreatic line easily on your drawings, just on a spreadsheet. Okay, so this is the kind of things that you can do in a spreadsheet, and that's what we are going to work on next week. For today, to finish today, what I want to show you is where to go get that little piece of software, which is very, very useful. Let's- Okay. And we're going to. So LibreCAD, there's two places you can go get it. One is LibreCAD, where you can just download and install it. Or do what I did here, where, oops, show you. I think I have it here. Yes, I installed it via portable apps. So portable apps is a nice software set. You may notice that I use a USB stick that I placed there. You can, with portable apps, you can install a number of open source software, either on your computer or choose a location like a USB stick. And that software doesn't need to be installed on your local machine. It's designed to have all its configurations saved locally within app USB key. Okay, so this is how I can run these programs that are on my USB key directly from my USB key without installing it on this computer, right? So I have this set of software. And on my same USB key, I have different software. So these are my common, because LibreOffice is useful in all my classes, but also LibreCAD and Numeric. Okay, these are the basic software that can be useful anywhere. But then I can also have for specific courses if I need. Like for my drafting course, I also have some things like Inkscape and more graphic oriented little programs. Right? And that I can have a second menu like this, a second app on my USB key that I place. So without installing on my machine, I can carry with me a number of applications. So portable apps is a site that I highly recommend for you.
Excuse me, so this one, we can just like Google,
LibreCAD, yes, LibreCAD, this one is for the basic installation. You will install on your computer. It's only 32 megs when you install it, so you can copy that folder. Also, you don't need portable apps itself. Okay, you could just copy the folder into a USB key and run it. But portable apps lets you do things in a very useful, convenient way, right? So like this calculate
Excuse me, just so I can Google, put portable app and search.
Yes, I will show you. So see, this is a nice little calculator that I recommend. It's on portable app. But so LibreCAD, you can get directly from here, okay? Or you can just download and install it. It's available for different operating systems. And again, it's very small. Then you have portable apps. This, I highly recommend if you want to manage software, a little bit like you manage software when you have Linux on your computer. All of these are open source software and they all work in Windows. And apparently you can even keep, so you can keep it on USB stick, you could keep it on your Google Drive, Dropbox. You know, it's oriented to be usable for many. It's a very useful little little software. And you see, when you have your portable app installed, you can go and you can search for apps, install apps, get more apps by title or by category. So let's say you want to go by category, it will give you a list of what's available on the website. Once you have portable apps installed, so you can have accessibility, development, if you like programming. Stellarium, that one I use for surveying, for instance. Okay, so you see you have different, these are games, you have graphics and pictures, you have Blender. Krita, there's for internet things. So you have a lot of software available here that might be of interest to you. Okay, so I do recommend that. But otherwise, LibreCAD on its own is available through here, and it's very, very useful. So here I already have it installed on my USB stick. So this is what LibreCAD looks like. Okay, as you can see, it looks a lot like AutoCAD in many ways. The selection works the same. Going back, you get the crossing selection. This is a full enclosed window selection. So if you're not familiar with the selection mode, so here you have the tools to draw lines. It's much easier to learn how to use than AutoCAD is, but it's also much, much more limited, right? But it's still pretty powerful in what it does. So if I want to select like this, everything it touches gets selected. If I select this way, only what's fully enclosed gets selected, just like in AutoCAD. You have layer management here. You can add layers. Okay, and you can define blocks. Okay, have layer tree, block list, etc., etc. So a lot of things that you can do in AutoCAD, you can do here. You have a command line window. The command line is not as erase. So not all the commands are implemented in a way, but one thing that you can see. You do have the undo command that you can type, copy, unknown command. So I have to figure out all the commands. It's not as powerful as AutoCAD. It's not as intuitive for the command names as in AutoCAD. But once you get a few commands, you can also type them from here, and you can copy paste coordinates here. So it can be very powerful. But what I would like to, or what I usually use it is to define on a layer. Close. So, and then if I change my layer, I can have. Okay, so we can hatch. I like to use solid fill for that. Enable preview. So if I were to save this as an image, I would, don't worry, we'll go over it in detail next time with proper coordinates. We'll have a proper geometry. We'll build the dam, different material properties. We'll set up a sheet in our spreadsheet with this. And then this, I can say then export as image. And this is where we choose the X pixel map. Now, I should erase this. Let's make proper shape so we have an idea of what's going on. So let's select a shape. We'll go from 0, 0. Okay. To 10, 0. So it measures 10 meters now. Okay. To 0, 10. To minus 10, 0. And close. Did I not say it? Okay, so we drew this line with the dimensions that we chose. It's a square that's 10 by 10 by 10. Okay. And now if I say hatch, hatch. I should select first. Turn off the visibility of this and now export as image. Where? Well, here the resolution is 1. It's actually half. So if I have 10 meters, it will save 20 by 20. Okay, I never understood it. So see, the width and height is given here. If I say resolution is 2, so it actually, so it takes the value and it goes by that, okay, so it will increase. So by default, it takes half of the unit, but you can adjust it here. And once you have an idea, you know how big the squares are, okay? And usually you would say color, okay? And you can choose if the background will be white or black. So if I were to open that image, it's an image, but if I use, oh, do I have Genie here? Yep. Genie is my favorite text processor for plain text files. So if I open that file in as a text file here. Okay, file, open. Oh, it saved that PNG. Why did it save as PNG? Did I not say XPM? Sorry, that's my bad. File, export, XPM, square. Okay. Windows doesn't see these images. I thought it was funny that Windows was able to do it. Windows is very limited as an operating system. But see, as a text, you can see here just text. So the blank spaces are just dots. Okay, so it has a static XPM, that's just a comment, static car dummy, okay? And now we start, so it has 20, it's 20 by 20, 2 colors, 1 character per color. And now it says the 2 colors, so this is green, is character hashtag, and dot is FFFF, that's white. Okay, so you have the dot, then each line separated by a comma, so it's basically an array in itself. So it's basically a C array. This could be interpreted in a C code, which is basically probably how it's handled. Okay, so it's defined as a pointer. A pointer to a string. A pointer to a character string. So this is, you can insert that in, well, actually, if, let's say that you were using C as your, or C++ to code your basic program, you could just add into a source code the image with this, okay? And it could help you use the same techniques that we use in a spreadsheet to define arbitrary geometries, because that's one challenge sometimes if you implement your own code, right? As a programmer, as a student. You may be able to write the code, but then you hit the brick. How do I make this complicated geometry? Well, look at this. This is basically implemented as code in characters. So it's super easy to just load that image then. And you have a map of characters also in your code that you can assign properties to characters. So you would then loop to character by character and take one character and say, oh, I have these properties associated with that character. It's super useful as a little image format. Okay, but it's basically a text file. So I really love this image format here. Okay. And this is what we're going to use to import this in Excel, in a spreadsheet. It could be Excel, but we're going to use LibreOffice. And we can have as fancy a DAM as we want. Okay. And we'll know how many units, how many steps. And from our drawing, we will know how big we made it, right? But keep in mind that it does like, so it goes half a unit, whatever unit it is. And so here we use a unit as a meter. Is half a meter good enough resolution for our problem? Maybe it is, maybe not. If not, then we increase our resolution step so that it will break it down into more units. Okay? So next time we'll work on that. For today, we are done. So enjoy the rest of your evening. And I encourage you to explore both LibreCAD and yes, Genie, if you like to do programming or just, this is a wonderful little text editor. It's oriented to for developers. It does have syntax coloring for so many languages, and so if you look at the document, file type, programming languages, all these languages will be recognized, scripting languages, Abacus, ActionScript, batch files, Coffee script, JavaScript, Julia, Lua, Makefile, Meson, MATLAB, Octave. Markup languages, BibTeX, cascading style sheet, DocBook. It has a lot of abilities. Okay, can recognize different line endings. Okay, which can be, I mean, Windows is carriage return line feed, Linux is line feed only, and Mac is carriage return only. So everybody does it their way. Do you know why they have different line endings? You know why it's called carriage return and line feed? Okay. In the beginning of computers, right, when they were starting to develop interfaces, the first thing was to send to a line printer, to a typewriter, right? So you have carriage return means bring back the head to the beginning. And then line feed is exactly what you did when you
Next line.
the typewriter, right? So the typewriter was the basic output device, so it's carriage return, line feed. So because you needed to do both processes at the end of a line, the standard original end of line, which is what Windows uses by default, is carriage return, line feed. But in other computing environments, say, well, on the computer, I don't need both of these. I just need to mark the end of line. So they just chose one. And in the Unix world, it was line feed, and the classic Mac was just carriage return. And that's why if you try to open a file in Notepad, sometimes the end of line is not recognized in Notepad because Notepad is a very basic or text processor, right? That only works with Windows convention. So if you don't have carriage return line feed, it doesn't recognize the end of line, so you get all your lines one after the other.
Can Notepad plus plus?
I have never used Notepad because I have Genie, so if you have Genie, why use Notepad? Genie is superior.
That taught me to never use Notepad and to use Notepad plus plus.
I would tell you use Genie. It's superior to anything. Okay, you can actually, I don't know if Notepad can be linked to compilers. Shortcuts. This one, once it recognizes the language, if I say F5, it will run my basic compiler if I'm programming in BASIC. I can set, if I'm programming in C, I have the proper extension and so on. It will, if I press F5, it will compile using the C compiler. If I have HTML, it will run my,
Different codes.
yeah. Not in the same file, but yeah, you can have, Genie will handle all the languages it has there. You can
And you take, say like a compiler for MATLAB or C, whatever, okay? And I don't know how it would work, but have two different things that could all work together, different languages, because if it compiles it.
You can, there are wrappers for one language that. So you can have some code that basically reads code in another language and interprets it internally. Either interprets or pre-compiles it. Assembly, you can include assembly in most, like in C, C++, you could insert assembly code, right? If you wanted to. So
I only know Python and MATLAB, but I don't like MATLAB. So when someone sends me MATLAB, I just convert it in an online converter Python.
yeah, okay, well, that's one way to do it. Yeah, I've never used Python actually. I'm scared of the debugging stage in Python because there's no line end. There's no end of structure, so.
Sent me her code, and she likes to use the Honda environment. I like to use a different environment for different things, like the pandas and well, the code only works in the Honda library because sometimes they rely on some, I don't know.
On the number of spaces counted or something like that.
Yeah, or it's specific.
That's the problem.
This geophysical for tomography, they use a package called discretize, which is from the old Conda, and the new Conda doesn't call it discretize anymore. So you have to find the old Conda package, right? Anyways, it would be.
Yeah, it's the main thing that discouraged me ever from Python is the fact that there's no beginning of structure, end of a structure symbol. So you're formatting, so any accident, if you backspace by accident something, debugging that has to be a nightmare. I haven't had to debug, but debugging is the biggest problem in any programming. And Python seems to make it a nightmare to debug. I'm not gonna lie, that's what prevented me from exploring it because yeah, it's popular. It's popular, but with that debugging problem, I don't even. So yeah, I tried to migrate to other programming languages. Free Basic is not a bad compiled language, actually. It's very compatible with Quick Basic. So I highly recommend it, and yeah, you can compile it from Genie. But you can compile pretty much any language from Genie.
The result
I'll see you next time.
What?
I think I need to say this one.
coming up,
Pardon?
the result for the assignments for.
Yeah, I got number 2.
Enjoy the week.
Yes, this